All right, so the plan for today is I will go over a little bit more about the Gibbs sampler. We looked at, the majority, like the main parts of it on Thursday. Then we were left, I think, at the point that I asked you to do some extra exercises to make sure that you understand how Gibbs sampler can be coded up by yourself. So to start, I will just go through this full conditional posterior distributions really quick again. So this is the case. Remember that our data model is still a normal, and we're hoping to let mu and sigma, both of the two parameters, as random. Okay, and then the way that we're doing it is we have to give a joint prior, and right now it's being specified through equation 14 on the screen. In particular, we discussed it last time that we're doing independent priors. So the joint prior is pi mu sigma, but we actually break it down as pi 1 mu and pi 2 sigma. As soon as we do that kind of breakdown, you're assuming that these two parameters are independent. Okay? And then we're giving independent priors for each of those parameters. And specifically, we're giving the same prior distributions that we used to do it. Remember, when we have sigma as known and mu as unknown, then we give normal mu 0, sigma 0 for mu, and it turns out to be a normal conjugate prior for mu, right? And then on the other hand, if you fix mu and then only let sigma to be random, then if you give a gamma distribution, gamma alpha beta, for 1 over sigma squared, which is the precision, then it is also conjugate, meaning that the posterior distribution of 1 over sigma squared is going to be a gamma with updated parameters. So we do this as what we used to do, and then when you have two parameters as what we have right now, instead of deriving the posterior distribution jointly, we're actually going to derive something that we call full conditional posterior distribution. And we talked about the definition. When you're looking at one particular parameter, say for example mu here, full conditional posterior distribution for mu is everything is being conditioned, including the data and every other parameter. In this case, you only have one parameter left, so that's being conditioned. And we looked at how to derive it in an efficient way that we didn't have to go through all of the normal derivation again, because now if phi being conditioned, meaning it's a constant, the likelihood contribution and the contribution from the prior only has this pi 1 mu, right? And then that boils down to what we used to do when you fix sigma or fix phi, and then you do the derivation, which comes to this normal full conditional posterior distribution. Okay? And then on the other hand, when we are looking at the full conditional posterior for phi, then by definition, mu is being conditioned. And then that also means when you're deriving the full conditional posterior distribution, what matters from the prior is only this pi 2 sigma part, which of course is only from equation 16. And then that goes back to what we used to do when we fix mu and then only let sigma to be random. Okay, so that's why you get exactly the solutions as we used to do in equation 17 and 18. But we also talked about last time that even though the results are similar, they're really doing two types of inference. In the past, we're only treating it as a one parameter model, so meaning that the other parameter is fixed. You're not thinking about making inference about it at all. You're going to use, say, like a sigma, like the sigma from the sample, for example, to use it as fixed. However, here, we're definitely treating both of them are unknown. But we're sort of taking a shortcut that the joint prior is independent priors. So you get two separate priors for each of the parameter. And then we define this full conditional posterior distribution. And then we come to the same results simply because the contribution of the other parameter in the prior doesn't matter for the parameter that you're working with. Okay, say for mu, pi 2 sigma doesn't matter anymore in the prior. And then for sigma, pi 1 mu doesn't matter anymore. So you get the same results. So we talked about, okay, now we have those two full conditional posterior distributions and then how to make inference. So the key is what we call that you're going to do the process iteratively, and we call this as a Gibbs sampler. So for example, because we do have the full conditional posterior distributions of these two parameters. We know what they are. And we looked at, okay, so if you start with a particular parameter values, in this case, say mu0 and phi0 that you start with, and then based on, this is equation 17, equation 18. So based on the setup in equation 17 and 18, we know that to get a new draw of mu, I need the data, which is given, and then a particular draw of phi. Okay? So then I can take a draw of mu based on the value of phi, and then immediately to get a new phi, here, we're going to use the draw of mu that we just did from equation 17. Okay? And then in order to get a new draw of mu, you go back to equation 17, and then you use the value of phi that you just drew from equation 18. Okay, so you do this iteratively. So generically, for a particular iteration index at S, what you do is for mu S, you draw mu from its full conditional posterior distribution with your phi value from the previous iteration. And then the next step is you draw phi S given the mu S that you just drew. And this distribution is from, I should just say equation 18 and then equation 17, because those are the full conditional distributions that we derive. And then once you are done with this set, you are left with set of two parameter draws at this particular iteration. Okay, so you do it iteratively. And of course, I said that when you do it long enough, say capital S number of times, can be viewed. So now the sequence of this mu S and phi S can be viewed, but not yet, I should say, may be viewed as a dependent sample from the joint posterior distribution of mu. And then at the end of the day, later you're going to see that how can we make sure that we can get independent samples from them, because that will be the correct approximation to the posterior. So that's what we're going to talk about today. And lastly, I show you this sample code that I wrote. I specifically wrote it through a function called Gibbs _ normal. I went through line by line, just the general idea how you're going to do this function writing, in particular for a for loop that you're iterating through S from 1 to capital S. And then I talked about, well, you're going to get a mu 1. And then, for example, you're going to get a sigma 1 as well, I should say a sigma 1. And then you're going to draw your mu based on the mean and standard deviation that you computed. And then what you do is you update the beta 1 also for phi. And then you use R gamma to draw a new draw for this phi. Okay, and in particular, as you can see, this mu was what I just drew. So that was the link that I talked about last time that it's important to pay attention to. Okay, so then we stop here as exercise. So here, let's focus on exercise 1 for a couple of minutes. Here, I'm asking you to initialize the chain, like the MCMC or the Gibbs sampler. Instead of, so previously, the sample code copied below here is you're initializing using phi. Okay. So that's why you draw mu first, and then use the mu that you just draw to get you phi. Okay. So now I'm asking you, we stopped here last time. I hope you spent some time thinking about this over the weekend, but if you haven't, now is the time to try to edit the code in a way that you are able to initialize the Gibbs sampler using mu init. Okay. And if you don't know what value to put, so here phi underscore int was 1. So maybe let's just keep consistent. Use the initial value of, let's say, let's 1. Let's do 1 as well. Okay, so this was this should be the initial value that you're going to use to change your code and update it. Later today, you're going to see that, well, if your Gibbs sampler is really mixing well, approximating the posterior, the initial value doesn't matter. Okay, if you run it long enough. So that's why I'm doing it pretty like freely in a way that, okay, let's just try to have one. But if you want to choose other values, you're welcome to do that. For now, let's just be like same on the board, so later when we do the demo, it will be the same. Okay. So let me pause here for a few more minutes so you can try to update the code in the way that you are able to understand the Gibbs sampler, and then we're going to look at it together really quick. Okay. Yeah, a quick hint here, I guess, would be useful is, say here, remember we're trying to initialize the chain with mu init, so instead of phi, we should have a mu, and then later we're gonna get it into the input. So let's name this as mu underscore init, right? And then in the loop, so as you can see, in the loop, because earlier we started the chain with phi, that means we should draw mu first, okay? Because you start with the initial value. So that's why you see all of this for mu, and then all of this for phi, and then the last line is to store the parameter draw. Okay? So what I would suggest you to do is now we're starting the chain, I should say, and the Gibbs sampler with initial value of mu, then these two blocks will have to be switched, because with the initial value of mu, you're going to draw your phi first. Okay? And then, of course, the last line, saving the parameters, that will just stay there. Okay? So try that again, and make sure that you get all of the numbers right, and then try to run the chain to see if it works. And then, of course, you have to change this part as well, because that's the input of the initial value that you give. And I was suggesting let's all use mu init to be 1. Okay. Yeah, let's spend a couple of more minutes on this. I noticed that in exercise 1, at the end, I said that compare results to the existing results. So the way to extract what you have computed is in this out object. Okay, so once you run your function, you should be able to access the para, P-A-R-A, the matrix that is saved in the output. Okay, so if you're done with editing the code, you're able to actually check out the results and then compare against what we have as we initialize the chain or the Gibbs sampler with phi.
That's how that works. Mine, look at my address. It looks like yeah, she looks like mine. Mine really looks like this.
Okay, all right, so I will just do a quick demo here. I'm sharing my screen, and yeah, so this is what we have so far. That's the previous, the existing. Let me try to. So this is what we have so far, and I was suggesting what you need to do is change this line, right? Instead of phi, you start with a mu, and then I was also saying you should switch this to blocks, because when you start a new value, when you start the Gibbs sampler with mu, you should draw phi first, and then mu next. Okay? So what you're gonna do. So let's say this is exercise 1. So here, first change is instead of phi, I do mu, right? And in case I forget later, let me actually also update the input. So instead of phi, I have mu. And I'm starting it with 1 as well. And okay, so if we look at the logic of these function now, so we definitely get y bar, that's from the data, the sample size. We're still gonna have the the matrix called para, so we can save all of the parameter draws, and then we start with new initialized value. Okay? The logic goes now. Remember in equation 17 and 18, those are the full posterior conditional distribution. And if you have a starting value of mu, the first step is to draw a new feed, right? To draw a new feed, what do you need? You need alpha 1. Okay, so you can change it to there. You need beta 1. So these are the gamma parameters for the full conditional posterior distribution. Okay? And once you get there, you're going to draw a new feed. Right? As you can see, we don't really need to change anything other than switching the two blocks. Okay? So now this block gave me a new feed. Okay? And then once I have a new feed, what I do? I try to draw mu, right? And the way to draw mu, again, we know it's going to be from a normal distribution. We need to get the mean and the standard deviation from the full posterior conditional distribution. So again, I don't think you need to change anything. You just compute the mu1 from, I think this case is equation 17. You compute sigma 1, and then you draw a new mu. Okay? And the last line, you don't have to change it. You're saving it as mu and phi here. Some of you might want this to be like very consistent. You can say phi and mu instead. But whichever, make sure that you know like which column is for which later. Okay. And then of course down here you have your input, and then the list includes the data, and then also all of the like the parameters for the two prior distribution, and then you start. I thought I changed it, maybe I didn't. All right, should be new here because we're starting with new. Okay, yeah. So I think doing this exercise, oh, I changed out there. Anyway, doesn't matter. So I should be able to. Let's see. Let me just quickly run it so we know what we're doing. I have to load the data really quick. Okay, so data. And then you get CE data. I need to create the log. I think in the data set itself, there's. I can have it. Okay. All right. So I run this. So you see that now I get a new column. That's the log total exp loss q. So first of all, let me run what we used to have. Okay. And I will just save this output as output old, because later then we can extract it to compare the two results. Okay. So anyway, so what we do is we run the function and then get the input and then run this.
Professor.
Yeah.
In the updated one, I think for the beta one, when you initialize it, you need to use mu and nit instead of just mu.
Oh, okay. Okay. Good question. So I will, yeah, let me talk about that and then go back. Obviously, something was wrong with the code. So good point. So you're saying that here we need to use the nit, not the mu, right?
Yeah.
Yeah. The thing is, a good practice is actually always assign the mu in this function. Yeah, it is there. You're right. But you have to be careful, like you said. So the reason why I'm doing this is because later, I mean, in the loop, as you can see, is mu and phi. Like we're using it like through the loop. Every loop, like every iteration, we're using it. So I think it's a good practice to assign the value outside from the input, and then you can just let the loop run. Okay. All right. Good. So good. Anyway, so something was wrong with what I because of this. Okay, sorry. So let me run it again, and then okay. So now I have run my old, like output old, right? So I was saying that you are able to yeah. So the param code, I think, is in the output code. Let's do the frame. I'm trying to extract the draws. And I have some sample code online, like the one that I post, but I'm just trying to do it now. So I think I'm saving mu and phi separately. So to get it, and then, yeah. So now I have created this matrix called like para underscore O, and then I have a list of mu and then the list of phi. Okay, yeah. I'm using this later so we can compare. And in exercise 1, we talked about, okay, let's start the chain instead of with phi, we start with mu. So let me call this output mu. Okay. And let me run this. So everything else is like I name it. It's not good practice. You should always name everything else separately. But here, trying to do a quick demo. So the input and then, okay, good. And then the para mu, I'm trying to use this to extract this data frame, the draws from the new Gibbs sampler. And then in the end here, I name it so I don't get confused. Names out mu, which is, so I save mu and the in the same order. Okay, so I get it. And, okay, so now on your upper right, you will see two data frames. One is para new, one is para old. You can always, oh, I didn't name it well. Oh, para new. Right, so now I have para old and para new. So one thing you can do is to plot them or like summarize them to see just to, in theory, they should give you very close results. So I'm just going to do a quick summary instead of doing the plotting so we can save time. So for example, I want to see the mu. Okay, so what I can do, I do a quick summary from the old, like the first Gibbs sampler, and then I do a summary. Okay, so you see that these two are pretty close to each other. Okay, so again, this is trying to say that whichever you start first, based on the initial values. I mean, here, as you can see, that initial values probably won't matter that much either. Okay, we're gonna see like the details about this in a minute. But here, this is for doing exercise 1, that how can you get the code to run if you want to initialize your Gibbs sampler instead of starting with mu. All right, exercise 2. And then, for, I did throw in exercise 2, but let's not worry too much about it in class at the moment. But I do want to mention, because last time I think Ryan mentioned, okay, if you're gonna do 2 initialized values, you can do it. You can initialize the vector. But at the end of the day, you're really just using one of them, right? Because to get the Gibbs sampler to run, you just need one initial value. So you can try it. Say, for example, I was thinking, well, I'm going to start with initial like mu 0 and g 0. And then I can just write like one more line to choose whichever I'm going to do, like a 50% chance. And then you can run it just as you used to do it. Okay. All right, good. So that's how to code up your Gibbs sampler yourself. Okay. And again, as you can see, you can write it through a function, but the key, of course, is to, first of all, you need to get the full conditional posterior distributions first. And once you get them, the Gibbs sampler is pretty straightforward. Okay. All right. And lastly, before we go to the next topic, just want to talk about it like pretty generically that, of course, sometimes you're going to have more than 2 parameters in the model. Okay. So Gibbs sampler can work there as well, but as you have probably have imagined, you need to have the full conditional posterior distributions for all of the parameters. Okay, so here I'm generically talking about m, number of parameters. And suppose all of this are tractable, meaning that you can derive them. then of course you just gonna have extended Gibbs sampler that you have to update for each of the M parameters one by one. And then of course, say for theta 1, you're conditioning on all of the parameters at the previous step, iteration S, right? And then when you go to theta 2, you immediately insert whatever you have done for theta 1 as the block, just like what we did with mu and sigma. Back then we had 2 parameters. Now if you have multiple, you just do it sequentially. Okay. So when you get a new draw, that will be used for the next parameter. Say, for example, if we keep going for theta 3, you're going to use the theta 1 that you just drew and theta 2 that you just drew. Okay. And then eventually, when you get to theta m, it's going to be all of the thetas that you drew at your current iteration. So as you can imagine, remember like previously in the demo, we're like getting 1 block for 1 parameter. So you're just going to have m blocks. You just need to like a good, I guess, good exercise or good practice is to keep the comments well enough so you know that each block is doing what. Okay. I think I could have done a better job when I can like break it down even further so we know which part of the code is doing what. For your own reference, I think it's good practice to do it in the future. All right, so, okay, so that's the first